Okay. So welcome everyone to today's colloquium. So today's speaker is Ben Martinez, and he's a fifth-year PhD student at Clemson University, where he's advised by Dr. Shen Liu. And his research is mostly on the vertical coupling and ionosphere thermosphere system predictability. And he was one of the HAO Newkirk Fellows. He recently finished his time here. So he visited in 2024, and then he was here over the summer as well, primarily working with me. So I think many of you may have met him when he was here, and so he will talk today about the work he was doing as part of his Newkirk Fellowship here, and it's on quiet time ionosphere thermosphere predictability during SSWs. So go ahead, Ben.
Okay. Hi everyone. Thanks for that introduction, Nick. Yeah, so like Nick said, I'm just going to talk about what I worked on while I was at NCAR for my Newkirk Fellowship. Yeah, so the title of the talk is Quiet Time IT Predictability during SSWs and TIGCM. So we're looking at IT predictability, but this is predictability coming from the lower atmosphere, hence quiet time, during some stratospheric warmings. And we're doing this primarily with the TIGCM model. Okay, so first I'm just going to talk very broadly about IT forecasting and why it is difficult. So, okay, so IT forecasting is inherently difficult, and when I say that, I mean that like the intrinsic predictability of the thermosphere and like the MLT is actually much lower than other parts of the atmosphere, even lower than the troposphere. And the reason for that is that the energy spectrum for the MLT, it's very shallow relative to like in the lower atmosphere, which means that there's a lot of energy in very small scale waves, and then the errors in those small scale waves cascade very quickly to large scales as a result of like low densities and so on and so forth, which means that any sort of small initial perturbation is going to quickly grow very large, and that will erase your their predictive skill from your model. And then at the same time, the IT is also, it's not just sensitive to voice from below or above, but it's sensitive to both, which means that to accurately forecast the IT, you need also an accurate forecast of the lower atmosphere and like the atmospheric waves that propagate up and impact the IT region. And you also need an accurate forecast of the solar magnetic drivers, KPNF 10.7. And then getting either of those things even a little bit wrong quickly leads to very large errors as a result of the rapid error growth in the system. And that's just like the intrinsic issues with predictability of the IT system. Of course, there's also like other issues with there's just less data there than there are in other areas of the atmosphere, so there's less to assimilate and so on and so forth. But yeah, and so this talk we're specifically going to be focusing on just the predictability that's coming from below, as I mentioned earlier. So just a quick overview of what sudden stratospheric warming is. So it's a rapid warming of the polar stratosphere where it can increase temperature by about 50 Kelvin in a matter of days, and a zonal wind reversal. These occur roughly once every 1.5 years in the northern hemisphere, a major SSW at least, where there's a full wind reversal, and about once every 20 years in the southern hemisphere. And they're driven by upward propagating planetary waves, and they're important for this question of predictability, especially coming from the lower atmosphere, because they impact the entire atmosphere, including the ionosphere and thermosphere. And here are just some figures showing what a schematic that shows, some of the coupling processes that are going on during an event. And then here's a zonal wind plot from IGCM at 60 degrees north, where you can see the wind reversal that occurs in the stratosphere, and then the enhanced winds in the other direction in the MLT. And you can see kind of how long-lived this sort of event is. Okay, so sudden stratospheric warmings affect the whole atmosphere. So including the ionosphere, as I mentioned before. And this is all just background. So the sudden stratospheric warmings, they change the background wind field. As I mentioned, there's that wind reversal. And then those winds modify tides, and then the tides modify electric fields, which then, maps up to to higher altitudes, and then the plasma drifts themselves are modified. And then you get sort of a signature that looks something like what's shown here. So specifically, the SW2 and M2 lunar tides are amplified, and it creates these roughly 7-day long oscillations that you can see at low latitudes. So this is from a paper that Nick did in 2014. And what you can see here is this is sort of I would say kind of the characteristic response of the of TEC to a sudden stratospheric warming. So the SSW occurred around the 25th of January in 2009, and it sort of excites these waves that progress to later local times in ionospheric TEC. And then this is comparing, so these are two model runs of the same event. This one, he's removed the lunar M2 tide, and you can see that this signature kind of goes away or weakens, which just shows the importance of it in the system, in this sort of process. And then down here, this is the observational, this is what was observed by Hikomarka. So, and this 2009 event was, I think it was the first one that this relationship was noticed, and it was a very dramatic SSW, and so it kind of is sort of like the archetypal SSW that's used to study these events. So this is the ionosphere across SSW, and we're going to basically be seeing if we can predict something like this in our model. The thermosphere also responds to sudden stratospheric warmings. So again, the change in the background winds alters the mean meridional circulation, which modifies the distribution of O and N2. And then you end up with these mid to high latitude O to N2 depletions that can persist for, a week or longer following the SSW event. And then also, not only is this a response in and of itself, it's also, a pathway by which the SSW signal gets into the ionosphere, as O to N2 is, a source and sink for electrons, and that will change your ionosphere as well. So what's shown here, this is from Oberheide 2019. This is gold O to N2 observations. And then here we have latitude and day of year for a 2018 SSW, and you can see this black line shows the zonal wind at 60 degrees north, which is a typical proxy for SSW strength, and then you can see this big blue region that is co-located with the wind sort of reversal that was attributed to the sudden stratospheric warming. And then here is just a correlation map of the polar vortex strength with O to N2 anomalies. And what both of these are showing is that, so the response to O to N2, it's a global response, right? You see very strong response at high latitudes. This is an enhancement here and an enhancement here. At high southern latitudes, even though this is a northern hemisphere polar vortex response, a northern hemisphere polar vortex. And so, so the point is here that the SSW affects the ionosphere and thermosphere globally, and so being able to predict that response, you're getting a global prediction of. You should be getting a global prediction of the IT by accurately predicting your SSW. Yes. So okay, so that's why SSWs have a big impact, but if the SSW itself isn't predictable, then it's not really useful. All that we know is that there's going to be a big impact during the event, but not that we can predict it. But SSWs are predictable in the stratosphere. So SSW onset in the stratosphere can be predicted as many as like 5 or 10 days ahead of time. In some extreme cases, you can even get longer lead time predictions, but you can pretty consistently get a good prediction for many of these events with the hindcast that's initialized about 10 days prior to the warming. So if you look here, these are from ECMWF forecasts of zonal mean zonal winds at 60 north, which is again the proxy of vortex strength. The black line is the truth from era 5. And then these colored lines are the ensemble average of different initializations. And you can see that for this SSW, where the wind reversal occurred on January 5th, this hindcast that was initialized on December 24th does a very good job of capturing that wind reversal, which shows you that, in the stratosphere, these things really are predictable so long ahead of time. Then down here, this is from one of Nick's papers using a CESM2 WACM6 hindcast experiment. So it's using WACM6 to create a hindcast data set. What this is showing is the composite response of many hindcasts, 20 years worth of hindcasts in the stratosphere. So this is the black is the composite truth, and these are the composites of hindcasts initialized, X days prior to or following the onset of the event. And I think one thing I wanted to highlight from this figure is that so there's one question of being able to predict the onset of the SSW, but there's also a sort of second predictability enhancement, which is associated with SSWs in the stratosphere and below, which is that if you initialize a hindcast in the days following an SSW, then you get better short-term predictability, right? Like you see these things, these two hindcasts that are initialized right on and right after the SSW do a really good job of following the truth for about 30 days. So you're getting a really long window of forecast skill that's sort of opened by the stratosphere. And the reason that happens is because the wind reversal filters out waves, and then, like I said, the as you filter out some of those waves, the energy density spectrum becomes steeper because the larger, more predictable waves that don't, the errors don't grow as large, take up a larger portion of the energy spectrum. And so you get a more stable system like that. And then now this is from that same study. This is still the stratosphere, but CESM2 WACM6 includes the MLT. So this is a similar figure, similar composite, except looking at the MLT, and you can see that there is, to some degree, some skill that is retained even as you go to the MLT, which is, so much less predictable as compared to the stratosphere. Okay, so now we've seen that the SSW is predictable in the stratosphere. SSWs affect the whole atmosphere. So then the question is now, does that predictability extend to the whole atmosphere? Like that SSW associated predictability, does it extend into the MLT and into the IT, or beyond the MLT into the IT? This is a case study again by Nick. It's a hindcast experiment for that 2009 SSW. So what was done here basically is he just initialized a bunch of hindcasts, X days prior to the SSW event, and let them run freely after they, simulated some observations. Then they ran freely up to a point, and then you can see here. So the black line is again the TEC truth, and these colored lines are the hindcasts with the spread from different ensemble members. And if this depletion is caused by the SSW, so this is like a fixed local time, and this, if you just take a slice of those propagating wave plots I showed earlier, you have like a depletion in some local times and enhancement in others. If this depletion is associated with the SSW, then what you can see is that all of these are predicting a depletion. They don't necessarily get the magnitude correct, but they do get the timing pretty well. And then you can even get this, depletion after there. So what this is telling us is that at least for this one event, it does seem like you can have some, predictive skill that's gained from the lower atmosphere during an SSW. But like I said, this is one event, and this is kind of sort of a remarkable case. Like this is like the archetypal, SSW that people use to study the IT response. So the question is, to what extent are other SSWs similarly predictable, or like is the IT response to these SSWs predictable? And then so to answer this question, we used 23 years of CESM2 Wacom 6 hindcasts, so the same ones that I showed earlier, but instead we're using them to nudge the lower boundary of high GCM, and therefore turning those 23 years of hindcasts of MLT hindcasts into 23 years of ionosphere thermosphere hindcasts, and then we will look at that set to see if to what extent are these different SSWs predictable, and how predictable are they. So let me just talk about the setup of our experiment. Okay, so as I mentioned before, the lower boundary is the Wacom 6 hindcast. So the lower boundary is taken from the Wacom 6 hindcasts. Those hindcasts covered the years 2000 to 2023, only winters, which were October, November, December, January, February, and March. And in that time period, we have 14 SSWs that weren't exceptionally late SSWs, late March SSWs. So these hindcasts were initialized weekly, every Monday, for this entire duration. And they were initialized off of Mera, so they ran for a time forced by Mera with realistic forcing, and then on those Mondays, they would be allowed to run freely, and they would be allowed to run for 45 days. So there are 5 ensemble members per initialization, and they output T, U, V, and Z3, so the geopotential height, as a daily mean plus the 12 and 24-hour harmonic coefficients. So, real Wacom, of course, not real Wacom, but Wacom typically outputs many pressure levels that would be near the lower boundary of high GCM, which could be used for 4D nudging. But unfortunately, because this data set was used for something else, for other studies, just like MLT predictability, and they didn't intend to use it the way that we're using it, they didn't keep all those levels, so we can only do lower boundary forcing as opposed to full 4D nudging. So that's what's in the lower boundary. And now as for the high GCM hindcast, we took those lower boundaries and then forced high GCM. We ran high GCM with a fixed KP at 0.3 and fixed at 10.7, 70 solar flux units. And so in that way, we're isolating. So all the variability that's in our data set is coming from the lower atmosphere and internal dynamics. And then the baseline, so what we're comparing our hindcasts to, like our quote unquote truth, is high GCM, where the lower boundary is forced by Wacom 6, constrained by Mera 2. So it's not free running Wacom 6, it's like SD Wacom 6, constrained by Mera up to 50 kilometers. And that's like the closest thing we have to a truth for this validation set, since we are looking at just quiet time variability. Of course, in reality, the force from above is going to impact your predictability, but the idea here is that if you can't predict it in this sort of ideal case, then you won't be able to predict it at all when you start to erase predictability by putting in unpredicted solar and geomagnetic drivers.
Can I ask a question? Maybe just some very minor things. So in the Wacom 6, do you fix the KP and F10.7?
Nick,
they have some very variable solar forcing.
Oh,
but I think the assumption is that it doesn't, affect too much 100 kilometers.
okay. Yeah.
Yeah. Yeah, and please, any questions, especially at this part, because I know this is the experiment setup is kind of complicated. Please ask me and I'll clarify. So of course, like ideally, if you were doing this experiment and you had like unlimited resources, the way to do this would be not to couple one on top of the other, but to just like create hindcasts using Wacom-X, where you have the full, two-way coupled ionosphere and troposphere. But as you can see, 45-day lead time, 5 ensembles for initialization for 23 years. That's, about like hundreds upon hundreds of simulation days, like well over 100 years, I think. So it's just too expensive. But high GCM is not that expensive, and so that's why we do it in this way. And that's also, I think, the reason why until this point there hasn't really been a comprehensive study of event to event hindcast skill. Okay. So this is a little schematic just to further illustrate what we're actually doing. So like I said, we initialize, so we have some baseline truth. You can imagine this is like, your TEC anomaly at a fixed location, a fixed local time. And then you have, your time series, and then you run the hindcasts, at that point. And because the hindcasts are initialized off of Mera, and of course the baseline truth is nothing Mera all the time, then they should agree perfectly at the first step. But then with time, they're going to wander away from the truth. So to do our comparison, like to assess, I think I'll actually say that in the next slide. Yeah, okay. So then to assess the skill, we're actually not comparing individual ensemble members, we're comparing the ensemble mean. So we nudge every single hindcast ensemble member to high GCM, and then we take those things and those high GCM runs and combine them together, just average them together, and that's what's used to compare to the baseline. So the reason that we do that, ideally, to make this more computationally efficient and time efficient, you would just nudge the ensemble mean directly. However, the ensemble average, because they're going to disagree a lot, especially in the MLT. The ensemble average has much lower values, just like you average out a lot of noise, and then a lot of wave forcing just kind of goes away in the ensemble average. So you have to nudge each one individually before you do your composite. And then another thing is, so the other way you could make this more efficient and make this like more doable in Wacom-X would be to, instead of nudging every single hindcast, you only nudge the ones near the SSWs, like those are the ones you're interested at the end of the day. But unfortunately, S2S forecasting, where like this like longer time scale forecasting, like where you're looking beyond a couple days, these forecasts like this pretty much always need to be bias corrected. Like they have very strong biases where you change your background, your forcing, in this case from Wacom, from Mera to free running, and there's a lot of biases, and it sort of just like drifts to very unrealistic values, and they become kind of useless pretty quickly. So you have to apply a bias correction, where the bias correction is just you in our case, at each latitude, at each lead time, longitude, latitude, and local time, we take all of the we take the composite truth, and we calculate the difference between the composite truth and the hindcast, and then add that bias back on to sort of to get rid of that unnatural drift. So to illustrate what that looks like, here's an example of a TEC hindcast. So this is what comes directly out of the model at a certain location, and what you can see is it agrees on the first day, then it has this like jump, and then it goes down, and then it sort of stabilizes maybe down here, and then starts to go up again in a sort of realistic way. And if you looked at every single hindcast that we have, they would all have this behavior, which it's not physical. So wherever you look, you see that. So then we calculate our bias by basically just doing the average of all the hindcasts as a function of, lead time, where lead time is days since initialization. And then you add that bias, which is a very smooth curve because we have, hundreds upon hundreds of hindcasts. You add those back to your TEC, and then it starts to look more, reasonable. So this orange line is the TEC after we apply the bias correction, and then the green line, the green dotted line, is the truth. So you can see it retains that like short-term variability, but we've gotten rid of that, these long-term unphysical trends that are there. You can see this one's not actually particularly not particularly good forecast. It agrees for a day, and then it just, these anomalies aren't in the same direction at all. But at least it's the climatology matches. And this is this is, like I said, this is standard practice in like subseasonal to seasonal forecasting. One other thing to note. So like I mentioned, the Wacom 6 hindcasts, those only saved, like, for example, there was like limited pressure levels, and they also only saved the daily mean plus the 12 and 24-hour harmonics. In order to ensure like consistency, I downsampled the truth before nudging that to TiGCM as well, just to ensure that there was like consistency. So I also just took the mean and the harmonics and reconstructed it from the mean and those harmonics so that it was consistent. We're comparing apples to apples. So therefore the only difference now is just what's going in at the lower boundary. Okay, so now we're not looking at hindcasts yet. We're just going to look at our baseline truth run, because we need to make sure that the baseline truth is able to reproduce the IT response. Because if that can't produce it, then of course the predictions aren't going to get it either. Okay, so what's shown here is local time versus lead time, so day since initialization for a hindcast initialized, sometime prior to, in this case, the 2001 SSW. So this dashed line shows the SSW. Here's TEC. And then now we detrend TEC by fitting and subtracting a fifth order polynomial. And then what we're left with is those wave patterns that look like what was shown for the 2009 case that I showed earlier, like at Hikamarka, where you have like, this several day oscillation that progresses to later local times with days since SSW. And then now to make sure that this response is somehow associated with what's going on in the lower atmosphere, what's shown here is zonal mean zonal winds at 60 degrees north from that same hindcast. And then what's going on, and then the ionospheric response. So you shouldn't expect these to be one-to-one. There's not a one-to-one correlation between zonal mean zonal U and TEC at a fixed local time. But what you can see is that this depletion is associated with the reverse, like it does happen at the same time as that strong depletion in U. So then similar now we have ODAN2 for a different SSW. But now instead of local time, we have latitude versus lead time. So this is at a fixed longitude sector, in this case, 160 degrees west. And this is just what ODAN2 looks like. You can see the depletion already up here, but then when you detrend it, the depletion is much more obvious. And then again, now here we can see a very clear relationship between what's going on in the stratosphere, so what the polar vortex is doing, and what the ODAN2 ratio is doing in this case, right? So the winds go up, they go down, and ODAN2 does the same thing there. So what we have is that our baseline truth setup, it does have the TEC response that we expect. It does have the ODAN2 response that we expect, And so now the goal will be to look at our hindcasts and see if they show the same sort of response in, TEC and denote N2, or to what extent they do or don't. So now I'm going to show, okay, well, here are some circles where I circled the things that I was talking about. So now I'm going to just show you a couple of examples of hindcasts. Oh, wait, okay, no, I'm not going to do that yet. Before I show the hindcasts, I want to make one point. So now that I'm going to start looking at hindcast natural predictability, I just want to emphasize that we're interested in two separate timescales of predictability here. So first, we're interested in like that multi-day wave response, which is like a 3-day or 3-day, or it's like 3 to 7 day or to 10-day even wave, which you can see like in the TEC, right? It's that longer period sort of oscillation. And there are features associated with the IT response that are relatively long-lived, right? Like the ODN2 response has this long sort of depletion, and then the TEC has those longer waves. But at the same time, we are also interested in like day-to-day variability, so capturing the actual like next day changes. And then the reason that we're interested in that is because I mentioned earlier, there's like a window of forecast opportunity where after the SSW, if you initialize a hindcast, you get a much better prediction of those next day, next day, wiggles and so on and so forth. And so just like to illustrate what I'm showing here, this is just an example of a hindcast and a truth where you can see that the 3-day and longer period thing is very well captured, right? Like the dashed red curve, which is the truth that's been smoothed with 3-day rolling window mean, and the black curve, which is the hindcast that's been similarly smoothed, they agree quite well for these 14 days of the prediction. But the unsmooth version, these anomalies are almost like perfectly out of phase, right? You have a depletion enhancement. So if you like, applied all of the metrics to assess model scale here, what you would see is that if you didn't do any smoothing, this would be a completely failed forecast. But on those 3-day time scales, it is successful. So we're going to consider both of these scales separately. And then the difference in terms of processing is that for the longer term stuff, I smooth with 3-day rolling window mean. For those short term predictability, there's no smoothing applied at all after the detrending. So now for the next figure, we're going to focus on this like longer than 3-day sort of prediction. So these have been smoothed a little bit, I think. Okay. So this is just an example of what one hindcast sees. So the first row in both cases is the truth for ON2 and for TEC. And the second row is what the hindcast for hindcast initialized around like at that time, what it sees. So first, let's look at TEC. You can see that again we have this. The dashed line is the SSW, but again we have the wave pattern, and it is captured very well by the hindcast. So this hindcast is initialized a bit more than 5 days prior to the SSW, and we have this accurate prediction, at least in this location, for what looks to be like about 10 days. So we get a 10-day good prediction of those 3-day waves. So now if we look down here at the TEC anomalies at a fixed local time, in this case 17, so that's like right up here, you can see the magnitudes, not exactly right, but the direction and the phase and timing is essentially perfect. So I just use these hash marks to obscure everything after 15 days because, like I mentioned, we're comparing the ensemble average, and because the predictability at 15 days is essentially gone, meaning that the ensemble members are basically just wandering randomly around the climatology. So when you collapse them into a mean, you basically just get back to climatology, and this becomes sort of meaningless. So I'm just trying to highlight. This is where we're looking, is in this shorter term period. ODAN2 here is not as good, but it's not too bad, I would say. So if you look at the actual SSW event, there's this enhancement that occurs here around 40 degrees north, and we capture that in both. It looks like assuming it's not a coincidence, it looks like the ODAN2 overestimates the magnitude of that, but the timing again is correct. And then there's this depletion down here that is also captured with this feature maybe not being perfectly captured, but to some extent I would say this one is pretty good. But it's not perfect. And then over here, let's just to see why it's not perfect, I guess. This is what's actually going into the model at the lower boundary. So the black is the truth, and the red is the hindcast for the Wacom 6 that is used to nudge. So you can see that there are some differences, and those differences translate to the differences here that we're seeing. So it's not perfect, but it is a pretty good prediction. So here's I would say an example of one that's I think pretty good. And then I have another one. So here just I'm circling those key features. Okay, so now here's an example of a hindcast that I think is maybe less good. Okay, so, and this kind of shows some of the one of the big complications with doing this. So if you look at this, so again, this is our truth, and this is our hindcast. So they both do show an SSW-like response. I think they both have, the response is there. There is a SSW in both, clearly, but the timing is off. So you can see this is a negative anomaly. Here's a positive anomaly, positive, negative. So it's perfectly out of phase, which means that even though it does show an anomaly or a SSW response that it's sufficiently out of phase that means perfectly out of phase. So that means your forecast is actually actively misleading, right? It's telling you the opposite of what's really happening. So that shows you just how severe just a small phase difference can be when you're trying to assess how good these forecasts really are. So you could get, yeah, there is an SSW, but if your timing is wrong, then it's wrong. Is there a question? Okay.
No.
Okay, cool. And then over here is ODAN2, and this ODAN2, I think up until the SSW, they agree quite well. So it does there's this enhancement that's probably associated with the vortex, with the wind reversal, and it does capture pretty well, and then it's just kind of way off. Although on large scales there is some agreement. And then here you can see so again, like I said, this one looks actually quite good in the MLT, but this phase shift kind of kills it in the IT, where it seems to be doing a really good job of capturing the SSW, but it's just the timing is wrong, and that incorrect timing goes all the way up into the IT. Okay, so that was what I would say is a bad one. Okay, so now I apologize that this side is just text, but so now we're going to try to quantify things a little bit, but there's a few complicating factors. So the SSW response varies greatly by event and by location. So what we had tried to do initially was to, similar to what I showed before in the next MLT study, try to create an SSW composite response where we just sort of average all the SSWs and then average all the hindcasts and see how they agree. But because there was so much variation from event to event, when we tried to create that composite, the anomalies just went to zero effectively. And that's related to it's difficult to define what the perfect start date is for an SSW in the IT and so on and so forth. But it's very hard actually to build a composite like that. So we couldn't do it that way. And at the same time, that those the phase of those waves that you see, the local time waves, they vary a lot by location. So then it's different, depending on where you look, you get different speeds and different structures slightly, which also complicates things because you could average two in the same location and they just cancel out. But that also raises the question of like, can we quantify how much the predictability of the response varies as well by location and event? And so since we could do the composite, here's what we did instead to quantify things. So we took every hindcast that was initialized approximately 7 days prior to an SSW onset, and we classified them as either producing a good prediction or a bad prediction. And we did that at each individual grid point, each location. And then the way we assessed good or bad was by using a combination of the anomaly correlation coefficient, which is just the correlation coefficient after removing the climatology, because of course the climatology matches, so that really inflates your skill and it's not a useful thing anymore. A version of the Breyer skill score, which for our purposes, all that you need to know is that Breyer skill score basically assesses how often the hindcast and the truth agree directionally, like how often do they both have a positive anomaly in the same spot versus how often they have, opposite facing anomalies, and RMSE. So we, and this is a little hokey, I guess, but what we did is we looked at these hindcasts, many of them, and just kind of classified by eye whether we thought they were good or bad. And then we tuned these different thresholds until until they agreed with our by eye assessment. Like what is the ACC, Breyer scale, and RMSE that gives you what looks to me like a good prediction. And then for doing that, we were able to put each SSW, each hindcast has a good or a bad prediction. And then again, like I said, this is all for that 3-day rolling window mean after we've done our detrending. So this is like getting rid of the whatever day-to-day disagreement might be, really looking at those longer term sort of variability. Okay, so now I do that for all of our 14 events at each latitude longitude grid point, and then we are able to make a plot like this. So what this plot shows is the fraction of SSWs, so out of 14, where the prediction was good. So like, for example, right here, where we're, at 0.6 or above, this means that more than half of the SSWs that we looked at had a good prediction here. Alternatively, like over here in this region that's masked by the hatch marks, less than 20% of the 14 were actually good. And the way that we used the hatch marks was by doing sort of like a Monte Carlo type analysis, where we took 14 subsets of the other non-SSW hindcasts and just checked if those were leading to quote unquote good predictions based on the metrics above. And then if the fraction exceeded what we're getting from the SSW set, then we say it was non-significant, which means that like these are, to the extent that you can do significance testing with only 14 events, these regions you have like a significant enhancement in skill. So you can see there's a strong spatial dependence. So just because there is increased skill from the SSW and you can predict things, it doesn't mean you get a global gain in predictive skill. It's very localized in these like high latitude regions, kind of sort of just outside of the EIA, it seems, with some additional enhancements at high latitudes. So ODEN2, we did the same analysis, and the ODEN2, you can see that all the gains in enhanced predictability are coming from higher latitudes. At low latitudes, you're not really getting much at all. So my interpretation of this, I think, so for one thing, this agrees with the correlations that I showed before, where you do get a very strong ODEN2 response at high latitudes. But I also think that it could be that the predictability that we're getting here in TEC might be coming from this like ODEN2 pathway, like the chemical pathway to changing TEC, because ODEN2 is longer lived and it has this longer, predictive timescale. And I think that might be what's giving us these enhancements, whereas this thing might be more related to like E-region dynamo, as it is sort of near the EIA at the very least. Okay, so that's looking at like the spatial variations, but then we can also do a similar analysis, but looking on an event by event basis. So what's being shown here is the fraction of the globe at which you achieve good predictions. So for example, and blue is ODN2, orange is TEC, and the black lines are similar sort of significance testing by just checking other sets of 14 events. So what you can see is, like, so for this example, the February event, almost half the globe, you can get a good prediction preceding the SSW, which is a lot, because you can see like there's a lot of these non-significant regions, so it's kind of a lot. But at the same time, there are some events, excuse me, that aren't really offering much in terms of predictive skill globally. That doesn't mean there's no skill. It just means that it's only covering a very small localized region, and it's less than you get from just like these other hindcasts that are initialized at different times that have skill which is not related to the SSW. So that's what's shown here. And then now I'm going to switch to the, sorry, I'm a little under the weather. Now I'm going to switch to the short-term predictability. So before, everything had that 3-day smoothing on it to see if you can get the onset of the SSW. But now we're looking at no smoothing, so like actual next day predictions. So, okay, so what's shown here is TEC. Okay, I'm sorry, I'm gonna get a drink of water. I will be right back.
Okay. Yeah.
Okay, thanks. Okay, sorry.
No problem.
Okay, so as I was saying, so these are not smooth at all, right? So now we're looking at true like next day predictability. So what these are the like the skill curves, which show the decay in skill with time, with like time substantialization for different composites of hindcasts. So this is ACC anomaly correlation coefficient, and then in like tropospheric studies, a typical threshold for a good prediction is 0.6, where just like if your forecast has an ACC below 0.6, then it's not really considered useful operationally. But if it's above 0.6, then it does have some skill. In MLT predictability studies, the few of them that there are, that skill threshold is typically relaxed to 0.5, only because the MLT is so much less predictable than other regions of the atmosphere. So what this is I've grouped together, the orange is all hindcast initialized around less than 10 days after the SSW. The blue is, light blue is 10 days before, and then the purple is all initializations with some error bars as like our baseline. So what you can see is that for the hindcast initialized after the SSW, you do get an increase in skill. You increase your forecast skill horizon by about a day, maybe half a day on average, and it is a significant increase. So ODN2, like I mentioned, ODN2 is much like it evolves much more slowly than TEC. So in general, it has a longer forecast skill horizon, and it also gets like a slightly longer gain of about a day for your forecast skill horizon. And this is, I think, a kind of an important point. I do think that a lot of the TEC skill that you do get associated with SSW is coming from that chemical pathway, just because ODN2 does evolve more slowly. So even though ODN2 is often like not as important as the E-region dynamo effect in terms of driving TEC, like as a percentage, it might be that it is the portion that we can predict anyways, which means that even though it's doing less of the work in coupling the MLT to the ionosphere, it's doing the work that you can actually predict potentially. Okay, so this is at one location, right? You could do the same analysis all over the globe, and so we do that. That's what's shown here. So in the first row, we have the skill horizon in days for all initializations. This is just like when it crosses the 0.5 threshold for TEC node N2. And then for the second row, we have the skill horizon, but only for that set initialized just after the SSW. And then here's the difference. So what the difference shows where it's red, that means you're getting a gain from initializing after SSW, and blue means you're actually getting a worse prediction. And I think this is pretty interesting. So again, you're not getting a space like a globally the same gains everywhere. It's very localized. And the ODN2 is consistent with what we saw before, where a lot of those gains are concentrated at high latitudes. And there's a clear hemispheric difference in TEC, which is pretty interesting. And then another kind of thing to note here is that these maps look different than the maps I showed before for the 3-day smoothed, which just shows that on those different timescales, you're getting very different enhancements in skill or depletions in skill. So depending on what you're looking at, where you actually are able to get an appreciable gain in predictability. Just depends on which timescale you're actually interested in. Okay, so then now the question is, why are some good and some bad in the IT? And of course, there's a lot of reasons, and there are many studies that try to answer the question of why some forecasts. But I think the reason that they fail, at least in this study, in the ionosphere, thermosphere, is just based on how good they're doing in the lower atmosphere. So what I'm trying to show here is how skill in your hindcast, your lower boundary, is related to the skill that you get in the IT. So the top panels are maps correlating MLT wind at like these, kind of arbitrary locations with TEC skill and ODN2 skill defined by the autocorrelation coefficient. So it's like a correlation of correlations. And the bottom panel shows just like, I picked a spot and just showed a scatter plot. Okay, so what you can see here is that ODN2 skill is highly correlated with MLT zonal wind skill at these locations, which makes sense, right? So ODN2 is driven by like mean meridional circulation changes. So it's driven by like bulk wind, which means that there's like a very linear relationship between the skill in the lower atmosphere and then the ensuing skill in the ionosphere. TEC, on the other hand, that response is driven by particular tidal components, right? So that means that the relationship between like the winds, for example, and the ionosphere is highly nonlinear, right? Because it doesn't necessarily matter so much what the mean wind is doing. What matters is what different tidal components of that wind are doing, right? Like it's been showing SW2 and M2 are playing a very important role. And then of course, like the response is transferred like along field lines mostly, right? Which means that the skill would also, in theory, be transferred along field lines as well, so hence nonlinear, which is why you get much lower correlations when you do this very direct correlate U with TEC. So the point here is that for TEC, I think for one thing, you need what really you need is like accurate prediction of particular tidal components, or as opposed to just like accurate prediction of the mean wind. And alternatively, maybe you can get the mean wind wrong and get the tides right, and then you still get a good prediction. So that's what's shown here, and I think the lack of the skill or lack of skill in the ionosphere really does depend on the skill or lack of skill in the thermosphere. And it remains like a question for your study, like quantifying, like put numbers on like how much does error in one translate to error in the other. I think that would be an interesting thing to do, but I haven't done it. Okay, so that's everything that I have. The main points are that you have pre-onset predictability, where like 3 to 10 days prior to an SSW onset, you're able to accurately predict the phase of those TEC waves and the O2 depletions at middle and high latitudes. Post-onset, you get like a gain of about 1 day following for high-cast initialized after the event. But then importantly, every SSW is different, and so is like the predictability. And so there's like very strong event-to-event dependence on skill, and also spatial dependence on skill. And so these like gains that you get in predictive skill really do depend on where you're looking, and I guess like the kind of SSW that you're looking at. So yeah, that's what I have to show today.
Okay.
And if there's any questions, I'll happy to answer them.
Thank you, Ben. Are there any questions either in the room or online? Yeah.
I have a question on your hindcast example 1. When you said the TEC or the phase of TEC are kind of better predicted.
Yeah.
Yeah, I just wonder, because I cannot read the label of time there. I just wonder what's the period of the oscillation, potential oscillation. It's like days, in scale of days or
Days.
Okay. Like how many days?
So like if you look at like this trough to this trough, that's looking at like 4 to 14 to like 10 days. But I mean that's just by eye. Yeah. Does that sound like what you've seen, Nick? About like 10 days?
Yeah, I think that would be about right.
Yeah.
Is this 10-day scale like directly or related to the duration of SSW? Like say if this SSW event is about 10 days, next one is about like 2 weeks, then does this periodicity follows?
To be honest, I haven't checked, but I don't like, you mean like the duration of the wind reversal?
Yes.
I haven't checked them. I'm not sure, but I will say that the phase like being, I don't know, between like 5 to 10 days is pretty consistent across all these different events. So yeah, I'm not sure. I don't know if someone else has an idea, but I haven't checked that myself.
Yeah, thank you so much. I think it's very interesting.
Mm-hmm.
So Ben, I have a question. So this is more like on the physics, the mechanism, how the change in the TEC relate to the ON2, during SSW.
Yeah.
How these two are related, which one, what's the sequence of change?
For how O2 would impact TEC?
And how they, so like during SSW, what changes? I guess TEC is through the dynamo. It's more like through dynamo, right?
Yeah. So I mean, so I think TEC is going to be impacted. I think so. I would say it depends where you're looking, right? So I think that like the low latitude TEC response is probably modulated entirely, almost entirely by the dynamo. That's not to say that O2 isn't playing a role as well, but I think that the dynamo dominates. But if you look at different latitudes, like mid latitudes where you're outside the EIA and you're not really not as much, field aligned things going on, but there is a very strong O2 response, like up here. I would guess that I would guess that there you're seeing a larger role being played by the ODA-N2 changes. But I'll say that it's also that's kind of a guess. I don't think that's actually been like checked, or maybe it has, and I just don't know. But I don't know if someone has done like a map of dynamo versus chemical, the relative importance of them as like a function of local time and longitude. That's just my suspicion that at higher latitudes you have more of a role being played by ODA-N2, and I do think that's worth doing because, like I mentioned before, like the reason that I think the chemical pathway is overlooked is because like at low latitudes it is like playing second fiddle to the E region dynamo, but because ODA-N2 evolves so slowly, I think that there's more potential for predictive gains from knowing ODA-N2 and then how that affects TEC. Even if it's like only a smaller percentage, at least you can predict that small percentage.
Yeah, because I think the like the tides, the SSW during SSW, the tides impact on the ON2 should be, it's a small, in magnitude wise it's small, and it's slower, should be slow.
Yes.
So I'm just wondering, whether it is an impact for that the low latitude EC, impact on low latitude can be very quick, right? Through the dynamo. And then from that impact, it can impact the TEC through the wind, because when the wind blow from summer to winter, it blows through the EIA, which is a huge heating source. So it really changes that wind, and then that wind downwelling, that will change the wind too at mid and high latitude. So through this mechanism, it would be faster than directly from the tides, through the molecular diffusion, whatever. And then from that changing on ON2 at mid and high latitude, that can, impact TEC in that region. So from the time analysis, seems to be this is also a possible path.
Yeah, I think that makes sense. That's very interesting. Yeah. Yeah, I think I feel like and maybe I'm wrong about this, but I think there's the response of the ionosphere at like middle and latitudes to the SSW is maybe not as well studied as at lower latitudes, because it's a little bit less dramatic.
Right.
Yeah. That is interesting.
Are there any other questions? Anyone or online? No? Okay. Thank you, Ben, again for the nice talk.
Cool. Thanks, Nick.